Week's experiment's all about limiting reagents, so we're going to be reacting two reagents together in different amounts and seeing how much we're going to get and then what's going to be the limiting reagent. So I'm going to kind of walk you guys through an example problem. Just note these aren't the same values that you guys will be using for the post lab. Again, those values will be in the experiment video itself. So this is a typical problem you'd see like this. So using 15 mils of 0.5 molar calcium chloride and 12 mils of 0.65 molar sodium carbonate, how many grams of calcium carbonate will be produced? So a couple things we have to keep in mind. One of them is the formula for molarity. You guys should have done this on the last experiment too. So molarity is equal to moles per liter. And then another thing to keep in mind is the formula for moles. So we're going to use moles is equal to grams over molecular weight. So we've got these in our back pocket. So the best way to kind of go through these problems is to write down your givens first. That way you have them and you can kind of figure out how you're going to get from one point to another. So we have two reactants in this case. So one of them is the calcium chloride, and we used 15 mils, and the concentration was 0.5 molar. So you guys can see, based off this, we can at least get to moles we used here. And we can get from moles of sodium carbonate the same way. So for sodium carbonate, we have 12 mils and a concentration of 0.65 molar. So the way we'd get to moles here is we'd obviously rearrange this. So molarity equal to moles over liters. Write that again. You guys can see if we multiply liters on both sides, molarity times liters is going to equal moles. So the first thing we want to do is figure out how many moles we're going to use. I always say limiting reagent problems are similar to cooking a recipe and trying to figure out how many of that recipe you can make. So if you're baking a cake, for example, and the cake calls for 2 eggs and you have 5 eggs in total, well, you can make a total of 2 cakes. So it's going to be similar here, except we're not dealing with actual ingredients, we're dealing in moles. So first thing we have to calculate is how many moles of each of these we have. So find out how many moles of calcium chloride we have, how many moles of sodium carbonate we're going to have, and then we can use that information to tell how many moles of calcium carbonate we will make. So again, we're going to use this formula here. We're going to solve for moles. So the only thing else we have to do is we got to convert this mils into liters, because again, this formula uses liters. So we're going to move the decimal place 3 spots to the left. So this is going to be 0.5 molar times 0.015 liters, and that's going to give me moles of calcium carbonate. I'm going to draw a line keeping this separate. Same thing on this side, we have 0.65 molar times 0.012 liters. And if we do the math on both of these, we're going to get 0.0075 moles of calcium chloride. And for sodium carbonate, we get 0.0078 moles. So now that we have this, we can figure out which one of these is going to be our limiting reagents. Again, we want to find what we're going to run out of first, and then that's going to determine what's the limiting reagent in this. Because remember, we can't create or destroy matter. So the way we're going to do this is, first thing we got to do is compare our mole ratios. So if we look at this equation here, thankfully for us, all the stuff we care about in the reaction is a 1-to-1-to-1 ratio. So if you guys look, all 3 of these are 1-to-1-to-1. You can tell based off the coefficients that are in front, or if there isn't a coefficient in front, it's just 1. So you guys can see for every 1 mole of calcium chloride, I can make 1 mole of calcium carbonate. For every 1 mole of sodium carbonate, I can make 1 mole of calcium carbonate. So I can say that, if I have 0.0075 moles of calcium chloride, I will make 0.0075 moles of calcium carbonate. So I have 2 answers here, so which one's right? So it's going to be the one that gives me the least amount of calcium carbonate in the end. So like I said, for this example, it's fairly simple because everything's 1 to 1 to 1, so it's going to be whatever is the least amount. Because you guys can see, if it's all 1 to 1 to 1, like I said, if I had 0.0075 moles of calcium chloride, that's how many moles of calcium carbonate I would have. Same would be true vice versa with sodium carbonate. So I have 0.0078 moles of sodium carbonate, and that means I would make 0.0078 moles of calcium carbonate. Now, the reason it's whatever one gives us the least is when we do those comparisons and conversions, that's assuming we have excess of the other one. And all that means is, I'm going to assume, let's say, that calcium chloride I have 0.0075 moles of, and I have all the sodium carbonate in the world to react it with. Well, in that case, if I got 100% yield on that, I would end up with 0.0075 moles. Same thing would be true here. When we did this kind of calculation, we said 0.0078 moles of sodium carbonate reacted with all the calcium chloride it needed. It would only make 0.0078 moles. Now you guys can see, if we have both of these amounts, I'm going to use all the calcium chloride up. So if we reacted all this up, it's going to be minus 0.0075 moles. That means I would have produced 0.0075 moles of calcium carbonate. What it also means is I would have reacted another 0.0075 moles of sodium carbonate, because again, this is a 1 to 1 ratio. So for every 1 mole of calcium chloride I react 1 mole of sodium carbonate, and I make 1 mole of calcium carbonate. So you guys can see here, obviously if I react all of this is going to be 0. If I react all of this, we're going to have a little bit left. We're going to have 0.0003 moles. You guys can see, if we did this the other way around, if we said, sodium carbonate was going to be our limiting reagent, and we, subtracted the 0.0078, if we subtracted it from here, we would end up with a negative number, and you cannot have negative moles of something. You can have 0, you can't have less than 0. So in this case, in this example, calcium chloride will be our limiting reagent. So now that we know what our limiting reagent is, we can figure out how much of the calcium carbonate we're going to make. So remember the question up top, we wanted to figure out how many grams of calcium carbonate. We didn't ask for how many moles, we want how many grams. So thankfully, we can use this right here, and we can calculate that. So now we know we're going to make the 0.0075 moles of calcium carbonate, because again, everything that we care about here is 1 to 1 to 1. So if I have 0.0075 moles of calcium chloride, and that's my limiting reagent, that means I will make at most 0.0075 moles of calcium carbonate. So now we have moles. So if we rearrange this, moles equals grams over molecular weight. Again, we want to solve for grams. So if I multiply molecular weight on both sides, we get moles times molecular weight is equal to grams. So obviously we plug this in, we get 0.0075 moles times, we're going to want the molecular weight of calcium carbonate, which is 100. So we'll get 0.75 5 grams of calcium carbonate. And this would be my final answer for that. So the very last thing we need for this experiment is to calculate a percent yield. So a percent yield is very, very simple. It is similar to calculating a grade. And what I mean by that is what we just calculated here, the 0.75 grams of calcium carbonate. That would be if everything went perfect. That would be if every step of the experiment went exactly as it was supposed to do. There was no loss of, spilling a solution. You measured everything properly, and 100% of everything reacted together. You would get 0.75 grams. Now, real world, we rarely do have it go 100% perfectly. Things happen. People spill things. People don't measure things out properly. So we get an experimental yield, and then we compare it to what we call our theoretical yield, and that can give us our percent yield. So it's similar to a grade. You take a test, it's out of 50 points, you get a 45 out of it. Your grade would be 45 divided by 50 times 100. Same thing for percent yield. So percent yield in this case is going to equal our experimental over our theoretical times 100. So this would be our theoretical. Let's say we did this experiment, did it exactly like we said it was up top, and we only ended up with 0.70 grams. We'll call that experiment. So to do our percent yield, it's going to equal 0.70 divided by 0.75 all times 100. And if we do the math on that, that is going to equal 93.3 on to infinity percent. So pretty good percent yield. Now, the thing to keep in mind with percent yields in chemistry, you can go over 100% yield. But unlike a grade, that's not better. That's still an error that you have to account for. So that's basically